Today's Daily Dose of Math is the first in a series of videos where we find an algebraic model that will represent the increase in vaccinations for COVID in the province of Quebec. I teach 3 different courses where students have to make algebraic models. In Secondary 2, I teach Math 2101. In Secondary 3, I teach Math 3051, and in Secondary 4, I teach Math 4151. All 3 of these books are called algebraic modeling, and they teach the students how to make models from situations. But they teach it at different levels. To do this, I collected some data by going on the online newspapers as the province of Quebec was initiating their vaccination program for COVID. On January 1st of 2021, I found that 29,250 Quebecers had been vaccinated so far. I divided this value by the population of Quebec. For the population of Quebec, for this lesson plan, I am using 8,485,000, which is a rounded value from one of the most recent censuses. I don't want this number to keep changing, so I'm going to keep on using 8,485,000 for the population of Quebec. By dividing the number who had been vaccinated so far on January 1st by the population and multiplying by 100, I was able to get a percentage of the population who had been vaccinated. In the Secondary 2 algebraic modeling course, the students learned the form y equals ax for the straight line equation. Plugging the percentage who had been vaccinated on January 1st into this form and replacing x with 19, because January 1st was day 19 of the vaccination program, I was able to find an a of 0.018. Therefore, I have an equation y equals 0.018x. This is very much a simplification of the situation, but it's using the techniques that students in the Secondary 2 algebraic modeling course have learned. Plugging day 50 into this equation means replacing x with 50, and I get 0.9%. Day 50 will be February 1st. Right now it is January 7th, so what we're doing here is we are using the equation that we made to predict what percentage of the population will be vaccinated by February 1st. Our first attempt has 0.9%. But I had more data to work with. On January 6th, I checked again and I found that 38,984 Quebecers had been vaccinated by then. I used the same process to convert that into a percentage, and I got 0.459%. And then I used the same process to make an equation. I replaced y with 0.459 and x with 24, because January 6th was day 24 of the vaccination program. I ended up with a very similar a value, but not exactly the same. I got 0.019, which gives me an equation of y equals 0.019x. When I replace the x with 50, again, finding out the percentage who have been vaccinated by day 50, February 1st, this time I got 0.95%. It's not very different. Now, in the Secondary 2 course, the students don't learn how to make an equation using both of these points. So they have the choice of using the first point from January 1st or using the second point from January 6th. But they don't have the techniques yet for using both points to try to find a more accurate equation. So this is the best that they can do. Still, they have made a model for this situation, and they have made predictions as to what will happen by February 1st. Let's move on to the Secondary 3 level. In Secondary 3, the students learn a different form for the equation. It's not just y equals ax, it's y equals ax plus b. And they also have learned how to use the slope formula. In this situation, the slope formula will give us 0.0228 for our a value. But the a value isn't enough. We also have to find a b value, the y-intercept. Using the form y equals ax plus b, I take my 0.0228, my slope that I have calculated, and I plug it into the a position, and then I plug in one of the points from my table of values. This time I chose x equals 24, y equals 0.459. This leaves me with only b as my unknown, and I'm able to calculate a b of negative 0.0882. That gives me an equation y equals 0.0228x minus 0.0882. All of these values have been rounded, but I'm trying not to round too high because I want to retain a little bit of accuracy. If I replace my x with 50, again, February 1st is going to be day 50. I simplify, and this time I get a prediction that 1.05% of the Quebec population will have been vaccinated by February 1st. The secondary 3 students have a little bit more power to try to come up with an accurate model, but this isn't the only way they can do it. A secondary 3 student who's trying to do this as part of a question could use this as their model, but they could also say, I'm going to use a combination of the direct linear model that we learned in secondary 2, the one that gave us y equals 0.0198x, and the y equals ax plus b model that I'm learning on secondary 3. And I can say my model is a combination of these two different straight lines. This is another approach to algebraic modeling. Okay, let's move some of these calculations smaller and out of the way so that we have room to do some secondary 4 math. Alright, we're ready. In secondary 4 algebraic modeling, the students learn a couple of different functions. One of them is the exponential function, and the other is the quadratic. These students have different choices and more choices when they try to find a model for this situation. When we look at our graph, does it really look like the 3 points we have put on the graph so far form a straight line? Well, this is a matter of opinion. Some students think they do form a line that just happens to be a little crooked, and other students think, no, that's not a line. In secondary 4, the students learn the exponential function and the quadratic function, and both of those form a curve. And this graph could be seen as forming either of those types of curve. Let's look at the quadratic first. If we look at the quadratic in the form y equals ax squared, as it is presented in the Math 4151 Secondary 4 course, we can replace our y with 0.459 and our x with 24. We're doing a similar thing to what we did when we were dealing with the linear equation, but this form has an x squared in it. So we have some simplification to do, and we're able to calculate an a value of 0.000797. And that gives us a simple quadratic equation of 0.000797x squared. We can do the same thing that we did with our linear equations. We can replace the x with 50 for day 50, February 1st, and we can solve for y, and we end up with 1.99%. This means we're predicting that 1.99% of Quebecers will be vaccinated by February 1st. But that's not the only approach we can take because we have more data. We used day 24 for this one, but we can also use day 19. We can replace the x and the y with day 19 instead of day 24 in our table of values. That means the y is 0.345 and the x is 19. Simplifying, we end up with y equals 0.000956x squared as our equation. And then when we plug day 50 into that, we get 2.39% as our predicted percentage of Quebecers who will be vaccinated by then. So this is two different approaches to algebraic modeling using quadratic. Of course, my Math 4151 students would understand that we really don't have enough evidence yet to determine if this relationship is quadratic, because we don't have enough points in our table of values to do the second difference test, or the y over x squared test. But the great thing about algebraic modeling is it's a model. It's an attempt to reflect the situation with math. you're not expected to always be able to perfectly represent the situation with an equation. I'm going to make these a little smaller and move them out of the way so that we can try the exponential. The form for an exponential function that we learn in Math 4151 is y equals ab to the x. And we can replace the y and the x with the values in our table of values. This time we have to do it twice. On top, I put the point 24, 0.459, and then below it I put the point 19, 0.345. Then I can divide the equations. 0.459 divided by 0.345 gives me 1.3304. A divided by A cancels, and b to the 24 divided by b to the 19 gives me b to the 5. I can plug this into my calculator and find that b has to be equal to 1.0588. If, when brought to the fifth power, it would give 1.3304. Reminder, most of these values have been rounded. Plugging b equals 1.0588 into my form, I now have y equals a times 1.0588 to the power of x. But then I plug one of my points in. I chose x equals 24, y equals 0.459. When I do this, the only unknown is the a, and I can simplify and end up with an a of 0.1166. That gives me an equation, y equals 0.1166 times 1.0588 to the x. Again, I can plug x equals 50 into this for day 50, February 1st. This time I get a projected percentage of Quebecers of 2.03% who will be vaccinated by February 1st. The weakness in all of these models is we don't really have enough data yet. But all of them are good models because all of them are doing what a model should. They are using math to try to make a prediction based on the situation that we're studying. We will look at these results again on February 1st and compare them to the actual percentage that happened. Then we can judge our models. But what we can also do every day is we can look for updated information about the number of Quebecers who have been vaccinated, add that extra information to our table of values and our graph. This will allow us to try to make a better model, regardless of whether we're using the direct linear approach, the partial linear approach, the quadratic approach, or the exponential approach. The more data we have, the better chance we have to put together a good model and make a good prediction. Stay tuned and keep revisiting this problem with me, and then we'll see together how well we did with our modeling when we see the result from February 1st. That is today's Daily Dose of Math. Please like, subscribe, and share.